Imagine a cityscape of light forged in the death throes of a star, where magnetic fury twists matter into spiraling jets of radiation. This is the Lighthouse Nebula, a cosmic beacon where a pulsar, essentially a spinning neutron star, the size of a city but packed with the mass of a sun, spins hundreds of times a second, its magnetic field a trillion times stronger than Earth's. Now picture this: the X-ray glow from NASA's Chandra and IXPE telescopes reveals not just heat, but the dance of light itself, polarized like a lighthouse beam slicing through space. These images don't just show a star, they map its magnetic engine, a cosmic lighthouse beam bent by the extreme gravity of its neutron star core. What we're witnessing isn't just a stellar remnant, it's a laboratory of extreme physics, where particles race near light speed, and magnetic fields warp spacetime. This isn't just about a pulsar, it's about how the universe bends light, and how two telescopes, working in perfect harmony, are peering into the heart of that dance, unraveling secrets that could rewrite our understanding of magnetism's power across the cosmos. In the vast expanse of the universe, where stars are born and die in dramatic displays of light and energy, one of the most intriguing phenomena is the pulsar, a spinning neutron star with a magnetic field so powerful it can shape the very fabric of its surroundings. Today, we're exploring a recent breakthrough in our understanding of these cosmic beacons, thanks to a groundbreaking study conducted by NASA's Chandra X-ray Observatory and the imaging X-ray Polarimetry Explorer, or IXPE. Together, these instruments have revealed a startling new insight into a pulsar nestled within the Lighthouse Nebula, a glowing cloud of gas and dust where the pulsar's intense magnetic field has been found to influence the nebula in ways previously unimaginable. This discovery not only deepens our knowledge of pulsars but also sheds light on how these extreme objects interact with their environments, offering a glimpse into the dynamic forces that shape the cosmos. To begin, let's step back and understand what a pulsar truly is. A pulsar is the incredibly dense remnant of a massive star that has undergone a supernova explosion. What remains is a neutron star, a sphere no larger than a city, yet packing more mass than the Sun. These objects spin at astonishing speeds, often hundreds of times per second, and their magnetic fields are among the strongest in the universe, trillions of times stronger than Earth's. These magnetic fields act like cosmic lighthouses, channeling high-energy particles and radiation into narrow beams that sweep across space like a lighthouse beam rotating around a tower. When these beams intersect with Earth's line of sight, we observe the pulsar's regular pulses of light, hence their name. The Lighthouse Nebula, named for its association with this pulsar, is a region of space where the pulsar's influence is particularly evident. This nebula is a vast cloud of ionized gas and magnetic fields, illuminated by the pulsar's powerful emissions. For decades, astronomers have studied this region, trying to unravel the relationship between the pulsar and its surrounding environment. However, until recently, the full complexity of this interaction remained elusive. That changed with the combined efforts of Chandra and IXPE, which have provided a new perspective on the pulsar's magnetic field and its role in shaping the nebula. The key to this discovery lies in the unique capabilities of the two observatories. NASA's Chandra X-ray Observatory has long been a cornerstone of X-ray astronomy, capturing detailed images of high-energy phenomena across the universe. Its ability to detect X-rays emitted by the pulsar has allowed scientists to map the structure of the nebula and trace the pulsar's influence. However, Chandra alone could not fully reveal the nature of the pulsar's magnetic field. That's where IXPE comes in. Launched in 2021, IXPE is the first mission dedicated to measuring the polarization of X-rays. Polarization is a property of light that describes the direction of its oscillations, and by studying how X-rays are polarized, scientists can infer the orientation and structure of magnetic fields in space. This capability makes IXPE a revolutionary tool for understanding the magnetic environments of cosmic objects. When Chandra and IXPE combined their data, they uncovered a surprising detail: the pulsar's magnetic field is not as uniform as previously thought. Instead, it appears to be a complex, twisted structure that interacts with the surrounding nebula in ways that were previously unobservable. The X-ray data from Chandra showed the nebula's glowing filaments, which are regions of ionized gas heated by the pulsar's radiation. But the IXPE data added a new dimension, revealing the polarization of the X-rays, which provided direct evidence of the magnetic field's orientation and its dynamic behavior. This combination of images and polarization data allowed scientists to construct a more complete picture of the pulsar's magnetic field and its impact on the nebula. One of the most significant findings is that the pulsar's magnetic field is not a simple, straight line but rather a tangled web of magnetic lines that twist and loop around the neutron star. This complexity suggests that the magnetic field is not static but is actively reshaping itself in response to the pulsar's intense energy output. The twisting of the magnetic field could be responsible for the intricate patterns observed in the nebula's glowing filaments, which appear to spiral outward from the pulsar. These filaments, illuminated by the pulsar's radiation, are thought to be the result of charged particles accelerated by the magnetic field, which then collide with the surrounding gas, creating the luminous structures we see. But how exactly does this magnetic field influence the nebula? The answer lies in the physics of magnetic fields and their interaction with charged particles. When a pulsar spins, its magnetic field generates powerful electric currents that accelerate charged particles to near light speeds. These particles, moving along the magnetic field lines, emit radiation, primarily in the form of X-rays and radio waves. The direction of this radiation is determined by the orientation of the magnetic field, creating the characteristic beams that define a pulsar's lighthouse-like behavior. However, the recent data from Chandra and IXPE suggest that the magnetic field's complexity may also play a role in shaping the nebula itself. The twisting and looping of the magnetic field could create regions of higher and lower magnetic pressure, influencing how the surrounding gas and plasma are distributed and heated. This discovery has profound implications for our understanding of pulsars and their environments. For years, scientists have studied pulsars as isolated objects, focusing on their intrinsic properties such as spin rate and magnetic field strength. However, the Lighthouse Nebula study reveals that pulsars are not just isolated entities but are deeply embedded in their surroundings, with their magnetic fields actively shaping the nebula's structure. This interaction between the pulsar and its environment is a dynamic process, where the pulsar's energy output influences the nebula, and in turn, the nebula's structure may affect the pulsar's behavior. Such feedback loops are common in astrophysical systems, and this study provides a concrete example of how they operate in the extreme conditions near a pulsar. Moreover, the findings challenge previous assumptions about the simplicity of pulsar magnetic fields. While earlier models suggested that pulsar magnetic fields are relatively uniform, the data from IXPE indicate a more complex, three-dimensional structure. This complexity could have far-reaching consequences for our understanding of how magnetic fields evolve in neutron stars and how they interact with their surroundings. For instance, the twisted magnetic field may play a role in the pulsar's spin-down process, as the magnetic field structure could influence how energy is transferred from the pulsar to its environment. Additionally, the presence of a complex magnetic field could affect the emission of high-energy particles, potentially altering the observed radiation patterns and the way pulsars interact with their surroundings. The study also highlights the importance of combining different observational techniques to unlock the secrets of the universe. While Chandra's X-ray imaging has long been a powerful tool for studying high-energy phenomena, IXPE's ability to measure polarization adds a new layer of information that was previously inaccessible. By working together, these instruments have provided a more complete picture of the pulsar's magnetic field, demonstrating how interdisciplinary approaches can lead to groundbreaking discoveries. This collaboration underscores the value of missions like IXPE, which are designed to address specific scientific questions that cannot be answered by traditional X-ray observatories alone. Looking ahead, this discovery opens up new avenues for research. Scientists are now eager to explore how the complex magnetic field of this pulsar compares to other pulsars in the universe. Are similar structures present in other pulsar nebula systems, or is this a unique case? Additionally, the study raises questions about the broader implications of magnetic field complexity in neutron stars. How do these twisted magnetic fields form? What role do they play in the long-term evolution of pulsars? These questions are at the forefront of current astrophysical research, and the data from Chandra and IXPE provide a crucial foundation for future investigations. In conclusion, the study of this pulsar in the Lighthouse Nebula has revealed a fascinating new aspect of pulsar physics, the complexity of their magnetic fields and their profound influence on their surroundings. By combining the strengths of Chandra and IXPE, scientists have uncovered a dynamic interplay between the pulsar and its environment, challenging previous assumptions and deepening our understanding of these enigmatic objects. As we continue to explore the universe, such discoveries remind us that the cosmos is full of surprises, and that each new observation brings us closer to unraveling the mysteries of the universe. The Lighthouse Nebula, with its glowing filaments and the pulsar at its heart, stands as a testament to the power of science to illuminate the unknown, one discovery at a time. In the vast expanse of the cosmos, where stars are born and supernovae explode, there exists a region known as the Lighthouse Nebula, a celestial beacon that has captivated astronomers for decades. At its heart lies a pulsar, a neutron star spinning with such intensity that it emits beams of radiation, much like a lighthouse beam sweeping across space. This pulsar, now revealed in stunning detail, was studied by two of NASA's most advanced X-ray observatories, the Chandra X-ray Observatory and the imaging X-ray Polarimetry Explorer, or IXPE. Together, these instruments have provided a new window into the extreme physics of pulsars, offering insights that were once thought impossible. But how did scientists arrive at this moment of discovery? Let's trace the journey of how these missions uncovered the secrets of this cosmic lighthouse. The story begins with the Lighthouse Nebula itself, a region of gas and dust illuminated by the intense radiation of nearby stars. For years, astronomers have observed this nebula, but it was the detection of a pulsar at its center that transformed it into a focal point of study. Pulsars are among the most enigmatic objects in the universe, remnants of massive stars that have exploded as supernovae, leaving behind incredibly dense, rapidly spinning cores. These neutron stars possess magnetic fields trillions of times stronger than Earth's and rotate hundreds of times per second, emitting beams of radiation that sweep across space like a lighthouse beam. When these beams intersect with Earth's line of sight, they create the characteristic pulses of light that give pulsars their name. However, studying these objects requires instruments capable of detecting the faint, high-energy emissions they produce. Enter Chandra and IXPE, two observatories designed to peer into the universe's most extreme environments. Chandra, launched in 1999, has long been a cornerstone of X-ray astronomy. Its ability to capture high-resolution images of X-ray sources has allowed scientists to study everything from black holes to distant galaxies. But while Chandra has provided invaluable data, it has limitations. X-ray emissions from pulsars are notoriously difficult to study because they are often obscured by interstellar material or masked by the intense radiation from their surroundings. To overcome these challenges, scientists turned to IXPE, a relatively new mission launched in 2021. IXPE's unique capability lies in its ability to measure the polarization of X-ray light, a property that reveals critical information about the magnetic fields and emission mechanisms of cosmic sources. By combining data from Chandra and IXPE, researchers could paint a more complete picture of the pulsar's environment, unlocking secrets that had previously remained hidden. The collaboration between these two missions was not a matter of chance. For years, astronomers had suspected that the Lighthouse Nebula harbored a pulsar, but confirmation required precise observations that could distinguish the pulsar's signal from the nebula's complex structure. Chandra's role was foundational. Its high-resolution X-ray imaging allowed scientists to map the nebula's structure and identify potential sources of high-energy emissions. However, without additional data, it was difficult to determine the nature of these sources. That's where IXPE came in. By measuring the polarization of X-rays, IXPE could reveal details about the magnetic fields surrounding the pulsar, which are crucial for understanding how it generates its intense radiation. The combination of Chandra's imaging and IXPE's polarization data created a powerful tool for unraveling the pulsar's mysteries. The timeline of this discovery unfolded over several years, beginning with initial observations by Chandra. In the early 2000s, Chandra's instruments detected faint X-ray emissions from the Lighthouse Nebula, but the data was inconclusive. The nebula's complex structure made it difficult to isolate the pulsar signal, and without additional information, scientists could only speculate about its nature. It wasn't until the launch of IXPE in 2021 that the puzzle began to take shape. IXPE's first observations of the region revealed a striking pattern. The X-rays emitted by the pulsar were highly polarized, a signature of the intense magnetic fields that shape its environment. These findings suggested that the pulsar was not just an isolated object but was interacting with its surroundings in ways that had never been observed before. As the data from IXPE accumulated, scientists began to notice something extraordinary. The polarization patterns indicated that the pulsar's magnetic field was not only incredibly strong but also dynamically changing, a phenomenon that could only be explained by the pulsar's rapid rotation and the complex interactions between its magnetic field and the surrounding plasma. Meanwhile, Chandra's high-resolution images provided a complementary view, revealing the intricate structure of the nebula and the distribution of high-energy particles around the pulsar. Together, these observations painted a vivid picture of a cosmic engine in action, a neutron star spinning at an astonishing rate, its magnetic field shaping the flow of charged particles and generating beams of radiation that sweep across space like a lighthouse beam. The process of analyzing this data was as meticulous as it was groundbreaking. Scientists spent years cross-referencing the X-ray images from Chandra with the polarization measurements from IXPE, using advanced computational models to simulate the behavior of the pulsar and its environment. These models helped them interpret the data, revealing how the pulsar's magnetic field influenced the surrounding plasma and how the emitted radiation interacted with the nebula's structure. One of the most significant challenges was distinguishing the pulsar signal from the nebula's background radiation, a task that required sophisticated algorithms and years of careful analysis. The breakthrough came when the team identified a consistent pattern in the polarization data that could only be explained by the presence of a rapidly spinning neutron star at the nebula's center. The culmination of this effort was the release of the composite image in July 2026, a stunning visualization of the Lighthouse Nebula and its pulsar. The image, a collaboration between Chandra and IXPE, combined Chandra's high-resolution X-ray data in purple with IXPE's polarization measurements in blue, creating a vivid representation of the pulsar's environment. This image did more than confirm the presence of the pulsar, it provided a new way to study its behavior. By analyzing the polarization data, scientists could now probe the magnetic field structure in unprecedented detail, revealing how it channels energy and influences the surrounding space. The image also highlighted the nebula's complex structure, showing how the pulsar's radiation interacts with the interstellar medium, creating intricate patterns of light and shadow. The significance of this discovery extends far beyond the Lighthouse Nebula. Pulsars have long been a source of fascination for astronomers, but their extreme environments offer unique insights into the fundamental physics of magnetism, plasma dynamics, and high-energy astrophysics. The ability to study these objects in such detail has opened new avenues of research, from understanding the behavior of magnetic fields in extreme conditions to exploring the role of pulsars in shaping their surroundings. Moreover, the collaboration between Chandra and IXPE demonstrates the power of combining different observational techniques to unlock the secrets of the universe. By leveraging the strengths of each mission, scientists have achieved a level of precision and insight that would have been impossible with a single instrument. As we look to the future, the study of pulsars like the one in the Lighthouse Nebula will continue to push the boundaries of our understanding. New missions and technologies will build on the legacy of Chandra and IXPE, allowing us to explore even more extreme environments and uncover the hidden mechanisms that drive cosmic phenomena. The journey of discovery is far from over, and with each new observation, we come closer to unraveling the mysteries of the universe. For now, the Lighthouse Nebula stands as a testament to the power of human curiosity and the ingenuity of scientific exploration, a reminder that even in the vastness of space, there are always new wonders waiting to be discovered. This composite image, released on July 9, 2026, shows the region around a pulsar, a neutron star with a strong magnetic field that spins incredibly fast, within the Lighthouse Nebula. The image contains X-ray data from NASA's Chandra X-ray Observatory in purple, X-rays from NASA's IXPE, imaging X-ray Polarimetry Explorer, in blue, and this part of our deep dive into NASA's Chandra and IXPE study Pulsar and Lighthouse Nebula focuses on, go deeper into the underlying science/physics/astronomy that makes this significant. Explain why it matters to our understanding of the universe, in accessible plain language. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. In the vast tapestry of the cosmos, pulsars stand as some of the most enigmatic and fascinating objects in the universe. These celestial beacons, neutron stars with magnetic fields a trillion times stronger than Earth's, have captivated scientists for decades. Their discovery in the 1960s marked a pivotal moment in astrophysics, revealing a new class of stellar remnants and challenging our understanding of extreme physics. But the story of pulsars is not just about their initial discovery, it's a narrative of how humanity's tools for observing the universe have evolved, allowing us to peer deeper into their mysteries. Today, NASA's Chandra X-ray Observatory and the imaging X-ray Polarimetry Explorer, IXPE, are pushing the boundaries of this exploration, offering unprecedented insights into a pulsar nestled within the Lighthouse Nebula. To appreciate the significance of this study, we must first journey through the decades of scientific progress that brought us here. The story begins in 1967, when Jocelyn Bell Burnell, a graduate student at the University of Cambridge, detected strange radio signals coming from a distant star. These signals, repeating with astonishing precision, were initially mistaken for a little green man's signal, a humorous but fitting nickname for the first pulsar ever discovered. What Bell Burnell and her advisor, Anthony Hewish, realized was that these pulses were not artificial but natural, emitted by a rapidly spinning neutron star. This discovery revolutionized astrophysics, confirming the existence of neutron stars, collapsed cores of massive stars that had undergone supernova explosions. Pulsars, as these objects came to be called, became the first direct evidence of neutron stars, a prediction made decades earlier by theorists like Lev Landau and Fritz Zwicky. However, the early days of pulsar research were limited by the technology of the time. Radio telescopes, while revolutionary, could only capture the radio waves emitted by these objects. This meant scientists could only observe the light pulses from pulsars, unable to probe their intense magnetic fields or the extreme conditions near their surfaces. The next major leap came in the 1970s and 1980s, when X-ray astronomy began to take shape. Missions like the Einstein Observatory and the Rosat satellite provided the first glimpses of pulsars and X-rays, revealing that these objects emitted not just radio waves but also high-energy radiation. This opened a new window into the universe, allowing scientists to study the extreme environments around pulsars and their interaction with surrounding matter. The 1990s marked a turning point with the launch of the Chandra X-ray Observatory, one of the most powerful X-ray telescopes ever built. Chandra's ability to capture high-resolution images and detect faint X-ray emissions transformed our understanding of pulsars. For the first time, scientists could observe the intricate structures around pulsars, such as their magnetospheres, the regions dominated by their magnetic fields, and the shockwaves created when their intense radiation collided with interstellar gas. Chandra's observations also revealed that pulsars are not just isolated objects but are often surrounded by nebulae, like the Lighthouse Nebula, where their energetic emissions interact with the surrounding medium. These discoveries laid the groundwork for more advanced studies, but they still left many questions unanswered. How exactly do pulsars generate their powerful magnetic fields? What role do these fields play in their emission mechanisms? And how do they influence their environments on such a grand scale? The 2000s brought another breakthrough with the launch of the Fermi Gamma Ray Space Telescope. Fermi's ability to detect gamma rays, high-energy photons emitted by the most extreme processes in the universe, allowed scientists to study pulsars in an entirely new wavelength. Gamma-ray observations revealed that many pulsars emit beams of radiation that sweep across space like lighthouses, a phenomenon that gives them their name. These beams, powered by the pulsar's rotation and magnetic field, can accelerate particles to near-light speeds, creating cascading effects that produce the gamma-ray emissions observed by Fermi. This discovery deepened our understanding of pulsars as cosmic particle accelerators, but it also highlighted the need for even more precise tools to unravel the complexities of their magnetic fields. After all, while gamma rays provided valuable insights, they could not fully capture the intricate dance of electromagnetic forces at play in these objects. Enter IXPE, the Imaging X-ray Polarimetry Explorer. Launched in 2021, IXPE is a revolutionary mission designed to measure the polarization of X-rays, a property that reveals how light interacts with magnetic fields. Unlike traditional X-ray telescopes, which measure the intensity and energy of X-rays, IXPE's unique instruments can determine the direction of the light's oscillations, providing direct information about the structure of magnetic fields in space. This capability is crucial for studying pulsars, as their magnetic fields are thought to be the driving force behind their emission mechanisms. By measuring polarization, IXPE can map the orientation and strength of these fields, offering a level of detail previously unattainable. When combined with the high-resolution data from Chandra, IXPE's observations provide a comprehensive view of pulsars, bridging the gap between theoretical models and observational evidence. The synergy between Chandra and IXPE is particularly significant in the context of the Lighthouse Nebula. This nebula, a glowing cloud of gas and dust illuminated by the pulsar's intense radiation, serves as a natural laboratory for studying the interplay between pulsars and their environments. Chandra's X-ray data has already revealed the nebula's intricate structure, showing how the pulsar's emissions shape the surrounding material. However, IXPE's polarization measurements add a new dimension, allowing scientists to trace the magnetic field lines that guide the pulsar's radiation. This combination of data not only enhances our understanding of the pulsar itself but also sheds light on the broader processes that govern the evolution of such energetic objects. The journey from the first pulsar discovery to today's cutting-edge studies is a testament to the power of scientific curiosity and technological innovation. Each mission, whether it was the early radio telescopes, the X-ray observatories of the 1970s and 1990s, or the gamma-ray insights of the 2000s, has built upon the last, expanding our knowledge of pulsars and their role in the universe. The Lighthouse Nebula, with its pulsar at its heart, represents the culmination of this progress. By combining the strengths of Chandra and IXPE, scientists are now able to probe the magnetic fields of pulsars with unprecedented precision, unlocking secrets that have eluded researchers for decades. This study is not just about understanding a single object, it's about advancing our grasp of the fundamental forces that shape the cosmos. As we continue to refine our tools and techniques, the mysteries of pulsars and the universe they illuminate will only become clearer, guiding us toward new frontiers in astrophysics. In the vast expanse of the cosmos, pulsars stand as enigmatic beacons, their rhythmic emissions cutting through the darkness like cosmic lighthouses. The recent composite image from NASA's Chandra X-ray Observatory in IXPE, released in July 2026, offers a glimpse into one such pulsar nestled within the Lighthouse Nebula. This image, a tapestry of X-ray data, reveals the intricate dance of high-energy particles and magnetic fields around a neutron star, a collapsed remnant of a massive star. Yet, while these observations provide a window into the universe's most extreme environments, they also highlight profound mysteries that continue to elude scientists. What secrets lie hidden within the pulsar's magnetic field? How do these cosmic engines accelerate particles to near-light speeds? And what role does the Lighthouse Nebula itself play in this grand cosmic drama? These questions, and many more, remain at the heart of ongoing scientific inquiry, driving researchers to push the boundaries of our understanding. At the core of the pulsar's enigma is its magnetic field, a structure so intense that it rivals the strongest magnets ever created on Earth. Neutron stars, born from the violent deaths of massive stars, are known to possess magnetic fields trillions of times stronger than Earth's. Yet, the exact configuration of these fields remains a subject of intense debate. Are they aligned with the star's rotation, or do they twist and spiral in complex patterns? The data from Chandra and IXPE, while groundbreaking, only partially illuminate this question. Chandra's X-ray images capture the overall structure of the pulsar's emissions, but they lack the precision to map the magnetic field's orientation. IXPE, with its ability to measure the polarization of X-rays, offers a crucial clue. Polarization patterns can reveal the direction of magnetic fields, but the data collected thus far suggests that the field may not be as uniform as previously thought. Some scientists propose that the magnetic field could be fragmented or twisted, creating regions of varying strength and direction. However, without higher resolution observations, these hypotheses remain speculative, leaving the true nature of the pulsar's magnetic field shrouded in uncertainty. Another mystery lies in the mechanism by which pulsars accelerate particles to such extreme energies. The pulsar's emission, visible as beams of radiation, is thought to originate from the interaction between its magnetic field and the charged particles it accelerates. However, the exact processes driving this acceleration remain elusive. The Lighthouse Nebula, a region of glowing gas and dust, may hold the key. Observations suggest that the nebula's structure is influenced by the pulsar's intense radiation, but the precise nature of this interaction is unclear. Some researchers hypothesize that the pulsar's magnetic field channels high-energy particles into the nebula, where they collide with surrounding material, creating the glowing filaments visible in the image. Others argue that the nebula's shape could be the result of a complex interplay between the pulsar's wind and the interstellar medium. Yet, the data from Chandra and IXPE do not provide definitive answers. While the X-ray emissions from the nebula hint at the presence of high-energy particles, their exact origin and acceleration mechanisms remain unresolved. This ambiguity underscores the complexity of these cosmic phenomena, where even the most advanced observatories can only provide partial glimpses of the grand design. The relationship between the pulsar and the Lighthouse Nebula itself presents another layer of intrigue. Nebulae like this are often the remnants of supernova explosions, but their connection to pulsars is not always straightforward. In some cases, pulsars are found at the centers of nebulae, suggesting a direct link to the explosion that created them. However, the Lighthouse Nebula's structure appears to be more dynamic, with features that may indicate ongoing interactions between the pulsar and its surroundings. The nebula's glowing filaments, for instance, could be the result of shock waves generated by the pulsar's wind, but the exact processes that shape these structures are still debated. Some scientists propose that the nebula's intricate patterns are shaped by the pulsar's magnetic field, which channels its energy into specific directions. Others suggest that the nebula's evolution is influenced by a combination of factors, including the pulsar's radiation, the interstellar medium, and even the gravitational pull of nearby objects. Without more detailed observations, these possibilities remain open, highlighting the need for further exploration. Beyond the immediate mysteries of the pulsar and its nebula, the study raises broader questions about the life cycles of neutron stars and their role in the universe. Pulsars are believed to be the remnants of massive stars that have undergone supernova explosions, but their long-term evolution remains poorly understood. How do they change over time? Do they eventually fade into silence, or do they undergo transformations that alter their emissions? The Lighthouse Nebula's pulsar, with its intense magnetic field and high-energy emissions, may hold clues to these processes. However, the data from Chandra and IXPE do not provide a complete picture. While the observations capture the pulsar's current state, they offer little insight into its past or future. This limitation underscores the challenges of studying objects that exist in extreme environments, where the conditions are so hostile that direct measurements are nearly impossible. Scientists must rely on indirect methods, piecing together fragments of information to build a coherent narrative. The study of pulsars also has profound implications for our understanding of fundamental physics. These objects serve as natural laboratories for testing theories of gravity, electromagnetism, and quantum mechanics. For example, the extreme conditions in a pulsar's magnetic field could provide insights into the behavior of matter under intense forces, potentially revealing new physics beyond the standard model. However, the data from Chandra and IXPE, while valuable, do not yet allow for such detailed tests. The pulsar's magnetic field, though intense, may not be strong enough to probe the limits of our current theories. Moreover, the interactions between the pulsar and the Lighthouse Nebula could offer a unique opportunity to study how high-energy particles behave in complex environments. Yet, without more detailed observations, these possibilities remain speculative, emphasizing the need for continued research. Despite the many unanswered questions, the study of the Lighthouse Nebula's pulsar represents a significant step forward in our quest to understand the universe. The collaboration between Chandra and IXPE has provided a new perspective on these cosmic phenomena, revealing the intricate interplay between magnetic fields, high-energy particles, and the surrounding environment. However, these observations also highlight the vastness of the unknown. The pulsar's magnetic field, the mechanisms of particle acceleration, and the nebula's dynamic structure all remain areas of active research, with new discoveries likely to reshape our understanding in the years to come. As scientists continue to refine their instruments and develop new observational techniques, the mysteries of pulsars and their nebulae will undoubtedly yield more surprises. For now, the Lighthouse Nebula stands as a testament to the enduring fascination with the cosmos, a reminder that even in the face of overwhelming complexity, the pursuit of knowledge remains an endlessly rewarding endeavor. This composite image, released on July 9, 2026, shows the region around a pulsar, a neutron star with a strong magnetic field that spins incredibly fast, within the Lighthouse Nebula. The image contains X-ray data from NASA's Chandra X-ray Observatory in purple, X-rays from NASA's IXPE, imaging X-ray Polarimetry Explorer, in blue, and this part of our deep dive into NASA's Chandra and IXPE study Pulsar and Lighthouse Nebula focuses on explain what's coming next, future missions, instruments, or observations that could confirm, extend, or challenge what we know so far. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. In this deep dive, we've uncovered 3 key revelations about the pulsar at the heart of the Lighthouse Nebula. First, the combination of NASA's Chandra X-ray Observatory and the IXPE mission has given us an unprecedented view of how a pulsar's magnetic field shapes its surroundings. While Chandra captures the high-energy glow of the neutron star, IXPE's unique ability to measure X-ray polarization reveals the direction and intensity of the magnetic field, like tracing invisible threads of cosmic power. This dual approach has shown that the pulsar's magnetic field isn't just a static structure but a dynamic engine, twisting and accelerating particles to create the glowing filaments we see in the nebula. Second, the Lighthouse Nebula itself is more than a backdrop, it's an active participant in this cosmic drama. The pulsar's intense radiation is colliding with the nebula's interstellar material, creating shockwaves that heat gas and accelerate particles, fueling the nebula's luminous dance. This interaction isn't just beautiful, it's a laboratory for studying how extreme magnetic fields and high-energy particles behave in space. Finally, this study underscores the power of multi-wavelength astronomy. By combining Chandra's detailed X-ray images with IXPE's polarization data, scientists are peeling back layers of mystery about neutron stars, objects so dense they warp spacetime and emit beams of radiation like lighthouses. These findings don't just expand our knowledge of pulsars, they hint at broader questions about how magnetic fields shape the universe, from star formation to black hole behavior. As we wrap up, remember that every observation like this one is a step toward answering humanity's oldest questions. How did the cosmos begin? What forces govern its evolution? And what secrets still lie hidden in the darkness? If you've enjoyed this deep dive, hit that subscribe button for daily explorations of the universe's greatest puzzles. And if you have a theory, a question, or a guess about what's next for this pulsar, share it in the comments. The cosmos is full of mysteries, and your curiosity is the next great discovery.